Okay, now we are gonna model in MATLAB a one rotor induction machine, and we are gonna use these parameters they are given here. So in the two previous videos, we figured out the voltage equations for our stator and a rotor in our stator reference frame, are an equation to find our mechanical speed when we use our power, and also we figured out that we have our electrical speed. If we want our electrical speed, we just need to multiply by the number of poles over 2. Okay, so just a little reminder, when we have IS and BS, this is actually the alpha beta component in our stator, and in the same IR is our alpha beta component in our rotor, and when we have ISR is our current in our rotor but in our stator reference frame. So here, what we saw in the videos is when if we want to do this, we just need to change this into multiply by an angle, and we will get this is gonna be as ISR, and the same here, this is gonna be, well, this is all the equation that we did, so that's how we're gonna get it. Okay, so first, to do the model, we are gonna have to figure it out, these derivatives, what are they equals to. So uh, we can see that we can move or we can move all of derivatives to one side and all the other expressions to the other. So for the first equation, we're going to have L1 di dt times is plus L0 di dt isr equals to ps minus r1 is. So remember that R1 is our resistance our in our stator. Okay, and we do the same for our other equations. We are gonna have we are gonna do it for this because it's in the stator reference frame, so we can do arithmetic with this one. So let's start with we want is. So is is right here. So R0 dt is plus R2 dt isr. Okay, now we have the other terms. We're gonna have VSR minus R2 resistance in our rotor ISR plus J omega L2 ISR plus J omega, this is omega R, so speed in the rod in the electrical, omega R L0 is. Okay, now we have two equations with two unknowns, so we can say here, for example, if we want is, we make these two equals by opposite, so multiply all this by L2, and we multiply all of this by L0. So this is gonna give us L2 times L1 is plus L2 times R0 SR equals to L2 that multiplies all of this. Okay, we do the same for the second equation, and now we know that we are gonna have to subtract, so we're gonna have minus L0 square times this minus L2 L0 TISR equals to minus L0 that multiplies all of this. Okay, so now we can get rid of this term, and we subtract these two and factor out the outs, so we are gonna get L2 times L1 minus L0 square times the ISCT equals to all of this. So now we just need to divide both terms by this, and we get our first equation for to find the current. So we have here our first equation. Okay, now let's do the same to get our ISR. So to get our ISR, we're gonna have to multiply we need to get rid of the IS, so we multiply on top by L0, and we multiply on the bottom by L1. Okay, so again, we're gonna have this, and we subtract. So we are gonna have L0 L1 plus L0 square this equals to L0 times all of this. Okay, and for the other side, we're going to have minus L1 times all of this minus L1 times this equals to minus L1 that multiplies all of this. Okay, now we can get rid of these terms. We do the same, we collect the outs. So we're going to have L0 minus L1 times L2 dt ISR equals to this. And now we just need to move this term here. We divide both sides by this, and we get our second equation. Okay, so now we have our equations for the IS and the ISR dt. So now we can look at the parameters. So let's start with that. We go to MATLAB. And here we're gonna put the parameters. Okay. So first they're telling us that we got a line voltage of 220. Then we have a rated frequency of 60. So okay, first we need the uh, phase voltage. So we need the peak, and this is gonna be equals to our line voltage over square root 3 times square root 2, because this was in RMS. Okay, now our phase frequency is gonna be equals to our rated frequency 2 pi times our rated frequency. Okay, so we have Rs. Rs is the resistance in the stator, so that will be our R1 in our equation, and it's gonna be 0.044. Rr is the resistance in the rotor, so it's gonna be our R2 in our equations. Lis equals to 0.55 millihenries to the minus 3. Ls here R. And so this is the self-inductance of the stator and in the rotor, 47 e to the minus 3. And we figured out last time that L1 is equals to LIS plus L naught. And we, first we need L naught, and L naught is 12.90 e to the minus 3. So now RL2 is going to be equals to LIR plus L naught. Okay. They are also telling us that we have a moment of inertia of 0.122, and that we have 4 poles. So this is no power, this is number of poles. Okay, so this is the information we can grab from here right now. Now we go back here and we grab our equations and open MATLAB. Just gonna have them here to be as a reference where I work. Okay, so first, what is gonna be our BS? We know that we are gonna have our sine wave. We said that our amplitude is BP, our frequency is phase F, and because this is gonna be our phase A, we don't have a shift. Okay, so this is A. We are gonna have also B, the same amplitude, the same frequency, but 120 degrees shift. So pi over 2 pi over 3. And this is our B. And now we're gonna do our C, and it's just shifted 4 pi over 3 from A. Okay, so this is our 3 phases. That's our input for our motor. Now we need to transform this into our alpha beta reference frame, And if you remember, that's our Planck's transform. So we are gonna have that this is equals to A plus 1 minus 1 half B. So let's put it over here. So this is our signal A, this is our signal B, and this is our signal C. Okay, and we're gonna have that this our alpha component is A minus 1 half B minus 1 half C, and this is gonna be our BS alpha. Now, if we want our beta component, is gonna be our B minus our C and this multiply by square root 3 over 2. So like this we get our Planck's transform, and here we have our PS beta. Okay, so now to get our actual phasor is gonna be this one plus J this one. So we are gonna get here a real to imaginary complex. So a real part is alpha and our imaginary part is beta. And this is gonna be our BS. Okay, so now we can put all of this into one subsystem, and this subsystem is just our ABC to alpha beta. Okay, so now we can do the same for our rotor voltage, but because this is a one rotor, we don't have a voltage in our rotor. So this is our, yes, this will be our IBC, but we don't have. But we still need a constant, we still need a alpha beta. So what we do is make this into imaginary and complex. So now here we have our PR. Okay, so we can start looking at our equations. We know that we are gonna have our BS okay here. We are gonna have our wait, did I copy the same equation twice? Here we have BS, yes, BS minus R1. So why do we have here this? Let me just check it. BS minus R1, BS minus R1, yes. Oh, okay. Here, there is a mistake here. I'm missing, here we are missing this term for our IS. So is this? Probably were telling me in the video that I made this mistake. Now we are talking. Now this is our equation for our IS. I was missing this term. So now I can put it here. I'm just gonna use an eraser. So gonna clean this up. Paste it here. Okay. So if I made this mistake here, I probably made it for this one too. So I'm just gonna erase this to make sure, I'm gonna make sure that this equation is right. Okay. So here we are also missing this term. Sorry about that. I'll copy this. Put it right here. Okay. And this is our equation for our ISR. I forgot to factor out that term too. Okay. Okay. Sorry about that. That's a mistake that should watch out for next time. Okay, so we are back here. Can delete this image. I'm gonna paste it here. Okay. Now I can make the point I wanted to say. That is that here we have BS minus R1 IS, and here we have BS minus R1 IS. So we are gonna have a gain of R1. R1 is our resistance in the stator, and we are gonna have it subtracting our BS. And here we're gonna have IS. So this is BS minus RS times IS. Okay. Now we can do something similar for I our inside of the rotor. So we know that we have L naught, we have L naught, sorry, we are gonna have P here, BSR minus R2 ISR plus J omega L2 ISR plus J omega L not ISR. Okay, so we can make all that part down here. So first we're gonna have PS minus R1 BS minus R2 I via. Okay, I'm sorry, it's just that it's a lot of terms. So we are gonna have here our gain of R, and here we are gonna have our I ISR. Okay, and now we need J omega R L naught ISR. So we need J omega. So for J omega, let's say that we have here real term imaginary. Here we are gonna have our J omega, our omega in electrical. So omega R. And now we know that this doesn't have a real part, so I'm just gonna connect it here to a 0. So this is our J omega R. And we multiply it by L2 ISR. So here we're gonna have a gain of L2 okay, it's gonna be multiplied, and this is gonna be multiplied by our ISR. So here we are gonna have J omega R times L2 times ISR, and that is this part over here. J. Now we do the same for this part, J omega R plus L naught IS. So we have J omega here, so we are gonna need this one, another again, forgot L naught. So this is L naught. Okay. This is multiplying J omega, and here we're gonna have IS. So here we have J omega R L naught times IS. Okay. So now we have these two portions, and this one and this one and this one and this one. So now we can subtract it from BR. So here we're gonna have a sum. So we are gonna have BR minus ISR times RR plus this term over here plus this term over here. Okay, so now we have here this one minus this one plus this one plus this one. Okay, so out of this we have our term PR minus RR times ISR plus J omega R times L2 times ISR plus J omega R L naught times IS. Okay, so now we can say that we have all the big terms. So if we want to get IS, we are gonna have to multiply this one times R2. So this one times R2. So gain L2, multiply here. And we subtract that. You're gonna have minus here. And we subtract it by all of this times L naught. So here we are gonna have another gain of L naught. Okay. When we subtract these two, we get all of this term out up here, and now we just need to divide by this term and we get our derivative. So we're gonna have again L2 times L1 minus L0 to square. So we're gonna have 1 over L1 times L2 minus L0 square. Okay. And what we get out of here is our DIS dt. Now we want our IS, so we just need to integrate this. But we can integrate it right away because remember this is a complex number. So we first need to turn it into its components. So complex to real and imaginary. And now we can integrate each components separately. And then we can join them again. To get our IS. Okay, now let's see which terms needed IS. So here, this one term that used IS. Okay, let's see down here, IS for this one too. Perfect. And now we need ISR. Okay, so for ISR, we're gonna do the same. We are gonna multiply these terms by R naught. So we have a gain of L naught. We have this multiplied by L naught now, and we are gonna have all of this times minus and we are gonna have L1. So all of this times L1. So we subtract these two. So we subtract this term over here minus this term over here. And now we divide it by this term, and we're gonna give our IDSR dt. So we're gonna have another thing here of 1 over L naught squared minus L1 times L2. Okay, perfect. So this is gonna give us our d ISR dt. Here it is dt. And just like in the other, we actually want is IESR. So we first separate it into each component. And now we integrate each component. After integrating each component, we can join them again. And like that, we get our ISR. And which terms needed ISR? We have one here. Okay. So like this. And we have another here. Okay, now we need to figure out our omega r. Now, if we look at our equation, we have that our omega m is equals to all of this. So we are gonna need the imaginary part of the multiplication of IS times ISR conjugate. So first, let's get this ISR conjugate. Here we have ISR. So, okay. So we know that this is the imaginary part of ISR. So we just have here this, another block. And we change this to negative. We have gain of -1 of this imaginary part. And here we're gonna have the real part. So this is ISR conjugate. Okay. So now we multiply this by IS, and where is our IS? It's right here. So here we have IS times ISR conjugate. Okay, so now we have this part. So we only care about the imaginary part, so we again use our blocks to get only an imaginary part, so we can use a terminator block for this one that we are not going to use. And our imaginary part we multiply by L naught. Okay, so by all of this, 2 over 3 number of poles over 2 L naught. So here we're gonna have again, so we have 2 over 3 times the number of poles over 2 times L naught. frames or not. Okay. So now we have our imaginary part of the multiplication times this. And we now subtract the low torque. Okay. So we're gonna have here a subtraction. This minus low by a constant that we are gonna call TL for low torque. Okay, so let's go back to our parameters. Here we're gonna add TL, and for now, because they're not giving us in the in the exercise, so we're just gonna call it 0 for now. Okay, so this is our low torque, and it's gonna be 0 for now. So when we subtract all of this by the low torque, we're gonna get our J omega. So this is our J d omega m dt. Now we only want the omega m dt, so we divide this by J, 1 over J. And now here we have our d omega m over dt. And now we integrate to get this was the omega m dt, and when we integrate we are gonna get our omega m. Now we don't care about this is our speed, okay, our mechanical speed, and to turn this into our electrical speed we just multiply by the number of volts over 2. So this is our speed in mechanical, and this is our omega r, our speed in electrical. And which term needed our omega r? We have it over here, all the way over here. For some reason it doesn't want to graph. Okay, perfect. Okay, get rid of this now. Okay, so this is a big mess now. So we can say that all of this that we did to get our omega is our mechanical equation. So all of this, but let me move this. Oh, it doesn't want to. Okay, it's gonna be like this then. Let's see how it looks when I make this subsystem. Okay, so this is our mechanical. Oh, but it should only return. This is our mechanical, but it should only return our omega 1. All of that was our mechanical. So we can have an scope here. To see our speed. Also I'm gonna add a display to see when it settles what is gonna be the value. So we are gonna call this speed, and we are gonna have also an scope for our current in the stator, and we are gonna add a scope for our current in the rotor. Now, here in our mechanical, when we were talking about the equations, we also we are now only talking about subtracting the low torque, but we could also subtract the losses due to the friction. So if we have here our friction constant B, we're gonna make this -1. So we have our friction constant and we multiply it by omega. This will be our loss in for friction, and we can put it here. And now here in our parameters, we say that also they are not giving us this, so it's gonna be 0. Okay, so now is the moment of truth. Let's try to run the model. Okay, so we can see the speed here. We can also see our rotor current here, and we can see our stator current here. Okay, so this is how we can model our one rotor induction machine in MATLAB. I hope this helps.